This is our last video for Chapter 3 and Chapter 4. It's going to be a fairly short one. I'm going to start with a bit of review. So if you're looking at a graph of a function, so we've got a function here. It does have some endpoints, so the graph does not go on forever. The domain and range, when you're identifying the domain and range from a set of values, it's a lot easier. You just list the numbers in the set. The domain would be the x values, and the range would be the y values. If you have a graph, it's a little bit trickier, just in that you have to identify which values for x there could be. Since it's a continuous graph, there's no breaks in the line here, then you can't list all the different x values because every fraction, every decimal, every irrational number is in there. So when you're listing the domain for a continuous graph like this, we're really looking at which x values work for this graph. And so we're looking at the least x value, -4, -5 wouldn't have anything there. So -4, everything in between, and the greatest x value, in this case 4, 5, it doesn't go all the way to 5. And then we would say everything in between -4 and -5. So the domain would look like this, sorry, -4, or -4 and 4. Everything in between. Since we have an open circle here and here, 4 is not included, -4 is not included, but we get super close. So we have -4, 4, and then we just say less than and greater than, not equal to. Range, same idea as the y values. We're going to look for the lowest y value, which is at -3, and the highest y value, which is at 5. And all the y values in between, it might be that there's more than one. That's okay for the y values. It's the x values that we can't have a duplicate on. And so the range would be from -3 all the way up to 5 and everything in between. And again, because of those open circles, you would not have an equal sign underneath that. It would just be less than and just be greater than. For these compound functions, when you have one function within another function, this fog idea, remember we take the function closest to the number first. So we look at this one first. We look at g of 2. So if g of x equals x cubed, we're going to do 2 cubed. So we're going to plug that number into this first function first. And so it really looks like this, where we take that g of 2 first, look from the inside out. 2 cubed then, because we're taking the function of whatever this is, and this is 2 cubed. 2 cubed is 8. So now we're taking the function of 8. We replaced g of 2 with 2 cubed, because that's what g of x was. We evaluated that. Now we're taking the function at 8. So we're going to plug that into the function f of x, 3x plus 1. The result would be 25. Similarly, if you were doing Goff, we would work from the inside out. We would do f of x first. So x would be 3x plus 1. We don't know what x is, so we just leave it as 3x plus 1. And then we're going to take whatever this is, 3x plus 1, and take g of that. So 3x plus 1 becomes the x. We're replacing x with whatever this is. Up here, we replaced x with 8, because that's all that was there. So it's 3 times 8 plus 1. Here we're taking 3x plus 1 and substituting it in for x here. So we end up with this. You would not expand it because we want it in its simplified form. So it would just be 3x plus 1 quantity cubed, like that. Okay, moving on. This is the last section then, or pretty close to the last section, direct variation and inverse variation. You might also hear this called a direct or indirect proportion. I believe in this text they talk about it as a variation rule. So a direct variation, the idea is that as one value changes, the other value changes in direct proportion to that other value. I'll give you an example. As x goes up here, for every 1 that x goes up, y goes up 2. If x goes up 1, y goes up 2. 1, 2. So we have a linear line, basically. And that's what we see here, y equals 2x. It's also one where the y-intercept is always 0. Because when x is 0, y is 0, and proportionally that would make sense. That would work. So a direct variation or an indirect proportion, y is 0. All the graphs that I have here are positive. However, you could have a negative. That would be the indirect. But typically, we just call any equation where it's y equals some number times x with no y-intercept, or a y-intercept of 0, I guess, plus 0, as a direct variation. I won't use the term indirect. And so up or down doesn't matter, positive or negative slope, but all these are direct variations. A direct variation is going to look something like this. And they have the verbal phrase here, so we're going to look at some different word problems, as well as the algebraic, what that means. So it says y varies directly with x. We're looking at y equals some number times x. Now this k here is essentially the slope m. They just changed it to a different letter because why not? We got other letters in the alphabet, let's use them. I don't really know why, but so it's y equals kx for a direct variation. K is the slope, so k is m, basically, when there's a y-intercept of 0. So y equals kx, so don't get confused with that k, that's the slope. S varies directly with the square of t, so now we have the square. Basically, it's the same idea, except instead of just x, we would have x squared, or the cube of z. So there's that directly proportional. U is directly proportional to the square root of v. So it's the same equation, except it could be with just x, the square of x, the cube of z, or the square root of v. Here's some examples. So I'm going to work these out on paper here in a second, but a question that you might be asked would be, y varies directly with x. Okay, so we know what that is. Y equals kx. If y is 15 when x is 5, we're asked to find y when x is 7. Or the bottom one here, v varies directly with the square of r. If v is 12 when r is 6, find v when r is 9. So let me look over at the document camera. Here we are. So the first one said that y varies directly with x. So I would say y equals, I'm going to use k, because that's what they use, times x. And we know that when y is 15, x is 5. So I'm going to replace that in here. When y is 15, x is 5, times 5. So, well, we can figure out what k is then. We're missing a variable here. We don't know what that constant of variation is. This is called the constant of variation. We can figure out that constant. It would have to be 3. 3 times 5 is 15. You could solve that by dividing by 5. And 5 divided by 5 is 1, so we have 1k left over. K is 3. Sadly, that's not what they asked us. They didn't say, what is the constant of variation? What is k? They said, when y is 15, x is 5, what would y be when x is 7? Well, now that we know what that constant of variation, now that we know what that slope is, we can say instead of y equals kx, well, actually, I'll put it again, y equals kx, we know that k is 3, and they told us x is 7, and they wanted to know what y would have to be. 3 times 7 is 21, so the answer would be 21. So for these types of problems, what you're basically doing is solving it twice. You're plugging in the information and you're solving for k, and then you're applying that same constant of variation, that same slope, to a new problem and getting the result. The second one said that v varies directly with the square of r. So slightly different in that we're not just doing y or v equals kr. It's v equals k times the square of r squared. But they told us that v was 12, and they told us that r was 6. So before we solve this, we should figure out what 6 squared is. We should evaluate a little bit further. So 12 equals k times 36. So now, maybe less obvious straight off the bat. So let's solve for k. 12/36. So I have this fraction here. When I divided, I created this fraction, 12/36. I know I can reduce that. I know I can divide them by 4. I think that's it. I don't think I can divide them by 8. So we divide by 4, divide by 4. 12 divided by 4 is 3. and 360 divided by 4 is 9. Looks like I can reduce a little bit further. So I could have divided both by 12. I didn't recognize that right away. So if I divide out both these by 3, I get, can you still see that? No, not quite. I get 1/3 equals k. So I could have simplified this, the greatest, the least common multiple, no, greatest common factor of these, greatest common factor would have been 12. I just didn't recognize that right away, which is fine. I still got to the right answer in the end, 1/3. I'm not done though. Not done. Maybe I shouldn't have boxed it, but I'm not done. I need to solve for v if r is 9. So v equals k r squared. I know what k is now. K is 1/3. I don't know what v is, but I know that r is 9. And it's squared, because it's r squared. So 1/3 times 81 is what I'm really trying to figure out. And that's going to be 27, I think. 27. So that would be my final answer, 27. I'm going to double check myself here before I, grab the calculator just to double check my mental math, 27. And that's so that's really how you do those. It's going to be very similar when we do inverse variations. Now, you will not be asked to graph inverse variations. These are exponential type functions. They're hyperboles. They're really kind of strange graphs to look at. We'll deal with it a little bit in chapter 6, but not too much. But an inverse variation, this is what it looks like visually, so you can kind of see what's going on. As one part of the function increases, as x increases, y decreases, but at a decreasing rate. And so how fast it's decreases as well. Or increases. As x increases here, y increases at an increasing rate. But this is what it looks like in terms of the equations. This is actually easier than dealing with it graphically. So it might say something like y is inversely proportional to x, or y varies inversely with x. It's the same type of equation, except instead of k times x, it's k divided by x. And so in this case, k is not like the slope. And so it's now k divided, some constant number divided by x, or some constant number divided by the square of x, or the fourth of x, or the cube root. So you can do it with anything, just like we did with the direct variation, except instead of times, it's divide. And really, that's the only difference between the algebra and direct variation and direct variation and inverse variations. So here are two examples, again, very similar to what we were just doing. Y varies inversely with x. If y is 8 when x is 3, find y when x is 48. We just solved them like that, except with a direct variation. The next one here is more of a real-world situation. The volume of gas varies inversely with the pressure that's applied on it. And they tell us the volume under a pressure of 30 kilograms per centimeter squared. And they ask what's the pressure, what would the pressure have to be to have a volume of 160 centimeters cubed. So let's look at that first one first. So the first one said that y varies inversely with x. So it'd be y equals k over x, k divided by x, not times. They told us that y was 8, and they told us that x was 3. So that we can solve a little bit. We can figure out what the constant is here. I can solve either by knowing that 24 divided by 3 is 8, and just knowing what that is, or I can multiply both sides by 3. 3 divided by 3 is 1, so I get that 1k is 24. So you can still solve it. So I have k, not the question though. The question was, what is y when x is 48? That was the question. So if I have y equals k divided by x there as my formula, I don't know what y is. I know what k is. And I know what x is, 48. Which I'm pretty much done then. Y equals 24 divided by 48. We have a fraction. I can reduce that. I should be able to divide them both by 4 and get what, 6? 8. I can divide them both by 8. So if I divide 24 divided by 8 and 48 divided by 8, I get 3, 3 6. Oh, it's half. Duh. Sorry. 24 48 is going to be half. So there we go. Y equals 1/2. We all have those duh moments where we are doing all this extra work and then see the answer and go, oh, I could have jumped straight to that earlier. All right, last one. The volume changes inversely with the pressure. So volume equals K divided by P. We know that the volume is 240. And we know the pressure is 30. So if I multiply both sides by 30 to get K all by itself, I would get 720, I believe. Oh, no, I might have missed a 0 there. Let's go with that. 30 times 240. Yep, double checked my math or my mental math with the calculator, 7,200. So that is the constant of variation in this problem. Again, I boxed it, but we're not done. So V equals K over P. Volume equals the constant divided by the pressure. So if the volume, we don't know the, oh no, we do know the volume. Volume is 160. So if the volume is 160, the question is, what pressure would need to be applied to that to get 160 as the volume? So we know the constant variation is 7,200 divided by something. Now in this case, we can't just multiply both sides by 7,200 because that's not what the problem says. The problem says that we're dividing by P. So we have two ways of doing this. I'm just going to do it one though. I've got this divided by P. So just like over here, I could multiply by whatever's in the denominator. That is important. You can only multiply by what's being divided. That's the inverse variation. Or sorry, not the inverse, I apologize, the inverse operation, the opposite operation. The opposite of divide is times, but it's divided by P. So you have to multiply both sides by P. So really I have P times 160 equals 7,200. So you have to do one extra step then. Divide by 160. So don't make the simple mistake of divide or multiplying both sides by 7,200. It's being divided by P. So you have to multiply both sides by P. And then you can divide by 160. So if you do 72,000 divided by 160, we get that the pressure must be 45. And I'm going to double check my units here. Pressure, kilograms per centimeter squared. Would have to be the pressure. P equals 45 kilograms per centimeter squared. So that's how you solve direct variation and inverse variation function problems. I'm going to stop there, and there's going to be one more video that deals with the project.